Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1984 witnessed the publication of a seminal work, The Fractal Geometry of Nature by Benoit Mandelbrot. This text, more than a scientific treatise, represents a paradigm shift, a re-evaluation of how we perceive and quantify the complexity inherent in the natural world. To fully appreciate Mandelbrot's contribution, one must journey back to the intellectual climate that preceded it, a landscape dominated by Euclidean geometry and a deterministic view of nature. Prior to Mandelbrot, scientific thought largely adhered to a framework that privileged smoothness, linearity, and predictability. Geometric forms were defined by idealized shapes, perfect spheres, flawless planes, and infinitely straight lines. These Euclidean precepts, powerful in articulating the fundamental laws of physics, struggled to capture the rough, irregular, and self-similar patterns ubiquitous throughout the cosmos: coastlines, mountain ranges, clouds, and even the branching structures of biological systems defied easy classification within the established geometric framework. The limitations of this approach were becoming increasingly apparent across diverse fields, from economics, where market fluctuations resisted neat mathematical models, to physics, where the behavior of turbulent fluids baffled existing analytical tools. The prevailing mathematical methods, primary calculus and traditional geometry, inadequately addressed the pervasive irregularity observed everywhere. Mandelbrot, a polymath with a deep appreciation for both mathematics and the visual arts, was uniquely positioned to challenge these dominant paradigms. His academic path, marked by a diverse intellectual background, including studies in mathematics at the École Polytechnique and a doctorate in mathematical sciences from the University of Paris, granted him an unusual perspective. Working at IBM, he began his exploration of complexity through the study of the statistical properties of communication noise. This led him to consider how irregularity, seemingly random disturbances, could be described mathematically. His deep dive into the study of chaos theory provided crucial insight. He sought to develop a framework to describe these complex, irregular patterns, leading to the development of fractal geometry. The core innovation of the fractal geometry of nature lies in its introduction and systematic exploration of fractals. A fractal, as defined by Mandelbrot, is a geometric shape that exhibits self-similarity, that is, its parts resemble the whole at different scales. This property, seemingly counterintuitive, provides a powerful tool for quantifying the complexity of irregular forms. Mandelbrot introduced the concept of fractal dimension, a non-integer value that quantifies the space-filling capacity of a fractal. Unlike the traditional Euclidean dimensions of 1, 2, and 3, fractal dimensions can take on fractional values, allowing for a precise measurement of the roughness or irregularity of an object. A line, for instance, has a dimension of 1, a plane has a dimension of 2, a coastline, exhibiting a far more irregular structure, possesses a fractal dimension somewhere between 1 and 2, depending on its degree of complexity. Mandelbrot's work was not merely theoretical, it was richly illustrated with compelling examples that vividly demonstrated the pervasiveness of fractals in the natural world. He analyzed the shapes of coastlines, finding that their intricate curves could be effectively described using fractal dimensions. He explored the geometry of mountain ranges, revealing how their rugged peaks and valleys displayed self-similar characteristics across various scales. He examined the patterns in turbulent flows, showing that these chaotic phenomena could, remarkably, be modelled using fractal techniques. His work extended to economic data, where he identified fractal patterns in stock market fluctuations, challenging the prevailing assumption of random walks in financial models. He investigated the branching patterns of trees, the structure of lungs, and the distribution of galaxies, all of which demonstrated fractal characteristics. The immediate impact of the fractal geometry of nature was substantial. It provided a new language and a new set of tools for scientists across disparate disciplines to describe and analyze complex phenomena. In computer graphics, the ability to model fractal shapes led to more realistic and visually stunning representations of landscapes, clouds, and other natural features. In image compression, fractal algorithms were developed to efficiently store and transmit complex images. In the field of finance, though identification of fractal patterns in stock market data led to new approaches to portfolio management and risk assessment, the impact extended beyond the specific applications. It encouraged a radical shift in perspective, urging scientists to see order within chaos and regularity within irregularity. The reception of the fractal geometry of nature was, initially, a mixture of fascination and skepticism. The concept of fractal dimension, the idea of non-integer dimensions, and the very notion that irregularity was not merely noise, but a fundamental characteristic of nature, challenged the established mathematical and scientific conventions. Some mathematicians initially viewed the work with suspicion, questioning the rigor of the fractal concept. Many scientists found its mathematical foundation difficult to grasp, however. Its visual appeal, combined with its explanatory power, gradually won over the scientific community. Influences on Mandelbrot's work were diverse: his early research on noise, his work with Claude Shannon on information theory, and the study of set theory inspired his approach to dealing with complex irregular data. The earlier work of Georg Cantor on set theory, particularly his explorations of infinity and the construction of the Cantor set, provided critical mathematical tools for the development of fractal theory. The contributions of Louis Fry Richardson, a pioneer in the study of quantitative approaches to war, whose work on coastline lengths, which varied depending on the measurement scale, provided initial impetus. The subsequent evolution of fractal geometry is a testament to its enduring legacy. The field has blossomed into a rich area of research, with applications in areas unimaginable at the time of its initial publication. In materials science, fractals are used to understand the structure of porous materials and to design new composite materials. In medicine, fractal analysis is employed in the diagnosis of various health conditions, including cancer and heart disease. In cosmology, fractal models have been proposed to describe the large-scale structure of the universe. The exploration of fractals continues, pushing the bounds of mathematical understanding and scientific modeling. The work of Mandelbrot paved the way for subsequent work by many researchers. Douglas Hofstadter, in his Pulitzer Prize-winning book Gödel, Escher, Ball and Eternal Golden Braid, used fractals to illustrate principles of self-reference and recursion. Michael Barnsley contributed significantly to the field and pioneered the use of iterated function systems, a powerful tool for generating fractal images. The development of chaos theory, particularly the work of Edward Ott, James York, and others, further advanced fractal concepts and revealed their critical role in describing nonlinear dynamical systems. Subsequent researchers built on Mandelbrot's vision and expanded the mathematical and computational tools for studying fractals. The fractal geometry of nature is more than a scientific text, it is a manifesto. It calls on us to recognize the beauty and the order inherent in complexity. It challenged the scientific community to look beyond the smooth surfaces and simple shapes that had, for too long, dominated the landscape. It provided a new framework for understanding the world, a framework that has reshaped our understanding of nature and the universe. Mandelbrot's legacy rests not only on his specific contributions to mathematics and science, but also on his profound impact on our way of thinking about organization, structure, and the intricate interplay of order and chaos. His work continues to inspire scientists and researchers, urging them to explore the hidden patterns of the world and, in doing so, to uncover the elegant geometry of nature.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.